that the nickel crystals, regardless what is the size of the raw material we use 5 micron powder, are too dense to participate in any LNR reaction. The structure of these crystals are, as already known, phase under cubic. So we had to find a way to modify the structure close to a C4 or PM3M structure, removing some of these atoms either from the surface or from the edges. So we really had to do something about the structure of the basic element that we use, create damaged or modified nickel. That's the structure close to what we're getting by the end of this process. We realized also that only some out of the 5 physical isotopes of nickel, 4 would participate in a reaction giving excess heat. Well, 1, nickel-61, was not willing to participate. And that saved us a lot of costly enrichment methods, which is also very good evidence for theoreticians to understand why this happens. And finally, we had to protect the modified nickels from the plasma ignition, as far as we already know that the temperatures on the surface of the glow jars are about 3,500 Kelvin in the surface and 14,000 Kelvin in the skirting. So we had to distribute these nickel modified powder structures around these jars and using a nickel foam of the same size with some porosity. In our case, we used 200 microns of porous. Here is a short picture of the nickel powders that were used, and this is the nickel foam that were used to hold them around. By the end, nickel, other components or agents that we use, and the ceramics that we use inside the reactor create of what we call nuclear or nucleic active environment, which is 48 square meters per gram. Now, then we have to find a solution for a problem where nickel and hydrogen need to be too close and not too close. Why? We know that red state atoms are short-lived. They are very elegant, and they can be lived only for a short period of time, nanoseconds, even though their size is relatively big. So the traveling path should be very, very carefully calculated. The Rydberg state atoms formed, we know since March 2012 that they form bonds with each other. They usually act in pairs or in lattice-like structures. And this is a very important development which was provided from another area, plasma physics, and it is important for LNR phenomena. Also, Rydberg state atoms of hydrogen need to travel towards the nickel environment, or the nucleic active environment that created for them. For this reason, we had to create agents. We had to use agents in order to help them in this journey. Zinc oxide, magnesia, and zirconia were some of the elements that we used to help the polarization of these creatures towards their destination. Well, for a period of 10 minus 13 of the section that we calculated, the Rydberg state protein is very, very close to the element. This is actually the time window we have where the Rydberg state nuclei are acting like a masqueraded neutron. And finally, Coulomb barriers, Coulomb forces between nuclei are almost zero during this very short period of time and within these lattice structures. So, LNR or fusion, or whatever you want to call it, reactions are possible, are theoretically possible. Now, what happens if we have nickel crystals vacancies, and these Rydberg state hydrogen atoms involved. Really nothing. Nothing happens unless we also do something about the nickel active environment itself. Really what we discovered is that we have to create these vacancies to open or close, like changing their shape at temperatures more than the debris temperature. In the case of nickel is on around 180 degrees. And using this technique, it's easy to get it. Now it is well known and well referenced and documented that nanocharges are created and traveling in waves with a speed of 5 kilometers per second between the nickel crystal vacancies. This is a well-known documented result, which is important because huge electrostatic and magnetic fields are created within these vacancies, and massive interactions occur between the Rydberg state atoms and the nuclear active environment. At the end of this journey, we have a band. We have an LNR bursting heating energy. And as long as we have the hydrogen atoms excited and polarized, this is our understanding of what we're really doing up there. But what type of LNR occurs? Even though this is a good question for the theoreticians in this field, we have strong evidence that about an answer whether strong forces or weak forces are involved for taking these low energy nuclear reaction place. Is that one of the two or both? Well, we have positive results from the analysis we did with XRF and ICP-MS in the nickel nuclear active environment and all the other agents before and after the reactions of transmutations. And there was not a line of transmutation. There are a lot of transmutations that we measured. Transmutations on the network of iron, cobalt, nickel, copper, zinc, potassium and calcium, and lithium, beryllium, and boron that were not present, the last were not present before the reaction. Where did they come from? Of course, it was very hard to identify short-lived species like hydrogen, deuterium, or tritium during this, maybe because the half-time or the measurements that we're using are not capable of measuring them. And we have to measure any high energy gamma emission out of the range of 50 keV to 300 keV. So I will give you just a few slides, 2 slides, about understanding this phenomenon. All the above give us strong evidence that we are dealing with a multi-stage dynamic reaction circuit, not with one reaction. And this reaction is heavily dependent on the initial conditions and the geometries involved. If you change one of the conditions or some of the geometries, you don't have the same results or you don't have any results. Also, we understood very quickly that we need feeder theories, not only new theories, but feeder theories that are consistent with the experimental results that we have. And of course, we committed ourselves months ago, and we repeat it here, that all of these data are available to the scientific community for further research or theoretical analysis after, of course, the licensing of the first generation products that we're dealing with, we're developing, and the completion of the building of new testing instruments like an online mass spectrometer that we're building that will help us to avoid too much theory. We have to stick on the data. Understanding the reaction as we understand really help us to control the reaction, or even controlling the reaction give us an understanding. So what we're doing actually in steps. First of all, we prepare and excite we prepare the nickel active environment, nickel, some other agents, and the ceramics around, and we charge it, and we excite it with heating. Secondly, we pump hydrogen inside the reactor where the NI exists, if it's not already present. And finally, we break the atomic hydrogen and excite it to its reduced state with very short controlled low charges. That's what we control. Then what we think, or we have good evidence that really happens. First of all, we have polarization of reduced state hydrogen atoms from the nanomagnetic fields created in the vacancies. Then we have the interaction of reduced state hydrogen, disguised protons. Still, we have they have brought into protons and electrons atoms, but in reduced state, and the proton looks like a disguised neutron with the heavy nucleus of the nion. Then we have this transmutation of heavy nuclei, followed by gamma emission and heat energy production. But we don't measure this gamma emission, where that goes. Well, there must be an absorption of that. Maybe, we are not sure, forming new elements from using heavy electrons. There is already one theory, not complete one, but there is a theory stating that. We don't know. Maybe that's what happens. There is strong evidence that this is not completely wrong. I'm talking about the LW theory, as far as we get transmutations of new species from hydrogen up to bottom. Still, we don't know which part of the energy, heat energy that we measure is coming from this phase or from this phase. We can only measure what we getting out in total. And that's why we need more instrumentation. That's why we are building more instrumentation, specially designed for LNR, to give that specific answer to the scientific community.
John, you have exceeded the time.
Oh, already?
Yes.
I will need a few more minutes for.
Okay, we'll give a couple minutes.
If it's not more improper, I would like to use some of your break.
There are other presenters, so
Well,
we'll wrap it up in a couple minutes, and then people can ask questions.
Engineering problem as a material problem, of course, had to face a lot of tech challenges, like introducing new technical ceramics that are inside the reactor. Reactors metallurgy, in order to give us the environment in terms of definitions versus magnetic fields, noises, etc. Safety-related material, nuclear media for data acquisition and control electronics that can survive in this environment. And National Instruments played a very, very important role developing such devices for us already. Well, there's another challenge that we have to build team building. Not team building only within our company, in our R&D teams, but team building with other companies or other institutions which really helped us to provide solutions either in materials or in the protocol development for our testing. Well, does it work? I told you a few things. Does it work? Well, first and second generation reactors were built for different purposes. Were not built, first of all, from the beginning to get the maximum code. First, we had to find out control and then get the code. We used a lot of recommendations and literature for calorimetry, which is important here. And we also have got very useful assistance, direct assistance from experts in the field and from international first level researchers and labs and the NINE for building robust protocols and measurement methods. And we created, of course, protocols, typically calibration and preparation, and run. All of them are logged using NI boards. Now, this is a first appearance of one of our reactors. Actually, it's a release 5 reactor, which consists of hydrogen control, high voltage input control, thermocouples attached inside the reactor or around the reactor, electric heating elements that preheat the reactor up to a point, hydrogen in pumps, coolant circuit, and high voltage blood magnesium interfaces like this spare plug like N. And of course, the PartII for gamma and photon detection. We set up gamma detection very carefully using potassium iodine sensors and other Geiger-Müller machines, logged again in national instrument boards, and calorimetry setup, which was one of the reasons, so big at the moment, it's one of the reasons that we not bring it so easily here. We're living actually on a very huge calorimetric environment with water tanks, filters, flow meters, digital flow meters, the reactor, the gamma detector, or the sensors that are measuring all electric input and output that we are getting, or input that we are consuming. By the end, this is the important thing. To get all these bars, every triggered reaction gives a burst. And as long as we excite the hydrogen, the burst really is ongoing. If we don't excite the hydrogen, then it's cooling down. So this is the triggering method that we use for reading temperatures inside the reactor. This is signal. And this is, of course, the pressure involved during these tests. And, of course, we have to monitor the energy produced by these signals, by these temperature bursts. You can see here the result of energy in and out, the plot of coolant flow, and by the end, how much energy we consume versus how much heat energy was got out from the reactor. As a result, we present our report these outcomes. Operating temperatures is around 180 to 849 inside the reactor. Output temperature range from 65 to 616 degrees Celsius at the moment. The maximum, of course, has to do with the coolant media that we use, which we don't want to change phase within this phenomenon, during this phenomenon. Each energy burst, like the one I showed you before, is 23 to 87 degrees delta T. And we consume something less than 1 to 2 watt-hours to trigger. The result is something between 16 and 92 watt-hours. Well, this huge difference depends on the different triggering level temperatures that we use. The higher level of triggering, the biggest performance we get. By the end of the day, because we're very dumb engineers, we get only from 1 to 8, 1 to 22 performance, as far as these reactors were not designed for proper calorimetry and performance. Also, we report here specific transmutations. This is only the XRF analysis, of course, and we have highlighted the elements that really give us also isotopic evidences and transmutations using not XRF but ICP-MS analysis. As you will notice, if you see them carefully, that they are very, very important predicted species coming out through these processes. Towards the industrialization path, Alexandros Xanthoulis gave some hints yesterday. Actually, we're still working on an industrial prototype build following the technical specs that were released November last year, which is a multi-reactor unit of 9 reactors, total 45 kilowatt. Industrial prototype tests and certifications are expected within the next months before the end of the year, and of course the setup of production and support lines in 79 countries around the world. Not by us, but also from other partners. Also, a parallel program is the design of new instrumentations for ELNR, which is actually an online real-time spectrometer around the Hyperion reactor. Then we can really trace what's going on inside the reactor the moment it happens. Of course, there are still more to come. And these are the important ones. That's why we're here, and that's why we're going to be in the ICCF 17 we don't have